Welcome back to our Juniper Data Center exam preparation series. Today we're diving into one of the fundamental topics you need to know. Traditional data center architectures, also known as multi-tier architectures. If you're preparing for your Juniper Data Center Associate certification, understanding these legacy designs is essential because they're still widely deployed and form the foundation for understanding modern data center designs. Let's get started. So, what exactly is a traditional data center architecture? Traditional data center architectures follow a hierarchical multi-tier design, typically consisting of three layers: the access layer, the aggregation or distribution layer, and the core layer. Think of it like a pyramid where traffic flows up and down through these distinct layers. This design emerged in the 1990s and 2000s when data centers were primarily focused on north-south traffic. That's traffic flowing between users outside the data center and servers inside the data center. Each tier has a specific role, and understanding these roles is crucial for the Juniper Data Center exam. Let's break down each tier, starting from the bottom and working our way up. The access layer is where servers physically connect to the network. These are your top-of-rack switches, often called TOR switches, sitting at the top of each server rack. The access layer provides server connectivity, connecting physical or virtual servers, basic services like VLANs for network segmentation, low latency, since servers connect directly here. Think of this as the entry point for all your compute resources. For redundancy, servers typically connect to two access switches using techniques like NIC teaming or LACP link aggregation. Moving up, we have the aggregation layer, sometimes called the distribution layer. This is where things get interesting. The aggregation layer aggregates connections from multiple access switches, provides redundancy through dual-homed connections, implements policy like access control lists, quality of service, handles layer 2 to layer 3 boundaries. More on this in a moment. Typically, you'll see access switches connected to pairs of aggregation switches for redundancy. If one aggregation switch fails, traffic automatically reroutes through the other. At the very top, we have the core layer, the backbone of the data center network. The core layer is all about high-speed forwarding, moving massive amounts of traffic quickly, interconnecting aggregation layers, tying everything together, minimal processing, no complex policies here, just fast packet forwarding, redundancy, typically deployed in pairs or more for maximum uptime. The core connects different aggregation pods and provides the path to external networks like the internet or wide area network connections. Now, here's something critical for your exam: understanding where layer 2 and layer 3 boundaries exist in traditional architectures. In most traditional designs, access layer operates at layer 2, using Ethernet switching and VLANs to segment traffic. Aggregation layer serves as the L2/L3 boundary. This is where routing typically begins. Core layer operates at layer 3, pure IP routing for maximum scalability. Why this design? Well, layer 2 provides flexibility for server placement and VM mobility within a VLAN, but layer 2 doesn't scale well across large networks due to spanning tree limitations and broadcast domains. So we route at the aggregation layer to keep layer 2 domains small and manageable. This is called a routed core switched access design. Let's summarize the key characteristics you should remember for the exam: hierarchical design, clear separation of layers with specific functions, oversubscription, more bandwidth at access layer than connections going up. For example, you might have 48 servers at 10 gigabits per second each, but only 40 gigabits per second of uplink capacity. This works because not all servers send traffic simultaneously. Spanning tree protocol, used to prevent layer 2 loops, but blocks redundant paths, limiting available bandwidth. North-south traffic optimization, designed for traffic flowing in and out of the data center, not between servers. Predictable forwarding paths, traffic follows known paths up and down the hierarchy. Like any architecture, traditional designs have both strengths and weaknesses. Advantages, well understood and proven, decades of deployment experience. Clear troubleshooting paths, hierarchical design makes problem isolation easier. Role-based segmentation, each layer has defined responsibilities, works great for north-south traffic, which was the primary pattern when designed. Limitations. Poor east-west traffic handling. Traffic between servers must hairpin up to aggregation or core and back down. Spanning tree inefficiency, blocks links, wasting bandwidth. Limited horizontal scalability, adding capacity means upgrading existing switches. Oversubscription challenges can create bottlenecks as server densities increase. VM mobility constraints, moving VMs across layer 2 boundaries is difficult. These limitations became significant as applications evolved toward microservices architectures, where server-to-server traffic, east-west traffic, became dominant. You might be wondering, if traditional architectures have these limitations, why study them for the Juniper Data Center exam? Great question. Here's why. First, many production data centers still use traditional architectures. They work, they're stable, and migration is expensive. Second, understanding traditional designs helps you appreciate why modern architectures like IP fabrics with spine leaf topologies were developed, which we'll cover in another video. And third, hybrid environments are common. You might have traditional architectures at the core with modern leaf spine pods for new workloads. The Juniper Data Center exam expects you to understand this foundation before moving to more advanced concepts.